In this video, I'll derive the general form for the energy balance on a closed system. Before I start with that, I should define what exactly a closed system means. For our purposes, closed means that no mass crosses system boundaries. No mass is crossing system boundaries. This does not mean that energy cannot cross system boundaries. And in fact, if we did not have energy crossing the system boundary, then we might argue about whether or not we can even write a balance on it at all, or whether or not it's just a boring, trivial problem. So when I think of a closed system, I'm thinking of a closed water bottle or something where nothing is going in or out. No matter is going in or out, but energy can transfer across the system boundary. Okay, so with that, let's start with our general balance equation. And in the last video, I said that generation, and consumption can immediately be discarded as not being part of this energy balance because we know that energy cannot be created nor destroyed. Let's kind of redefine accumulation to be, if we think about what accumulation is, if I accumulate stuff, that is a difference from one point in time to a previous point in time. So I'm going to choose to define the accumulation as the final system energy minus the initial system energy. Final minus initial. And if I think about input and output, if I take those terms kind of together and I think about it as a net transfer, I can define this as net energy transferred to the system. Transferred to the system. Where I've been very careful to define that to the system means that if I have energy transferred to the system, then I should have positive energy. So if my in is greater than my out, then I'm transferring energy to the system. But if my out is greater than my in, I can still define energy transferred to the system. It would just be negative, which would also make sense, meaning that energy would be transferred by the system to the surroundings. So given what I had defined in the last video about the types of energy, if I take the final system energy minus the initial system energy, I can take the sum of the forms of energy. So I'll call it E sub k at time 2 plus E sub p at time 2. I'm going to call this actually final, not 2. EK final plus EP final plus U final. I'll get rid of this, just do subscripts. Kinetic final plus potential final plus internal final minus kinetic initial minus kinetic potential initial. Sorry, potential energy initial. I'm having a very hard time speaking today. UI. And if you notice, it looks kind of clunky and not very elegant when I write it that way. So if I take final minus initial kinetic energy, there's another way that I can write that. If I just simply write delta EK, that looks a lot better. Delta EK plus delta EP. So this is the change in kinetic and potential energy and the change in internal energy. These three things summed together are going to be my accumulation. And if I take net energy transferred to the system, then by the two ways that I can transfer energy, this is going to be the sum of my Q and W terms. And just like that, it was easier than I had even anticipated. This is my general form of the closed system energy balance. And just like the mass balance, it is very deceptively simple. So it doesn't look like that tough of an equation, but figuring out what all these terms mean is the difficult part. Closed system energy balance. So we'll get to how to derive terms for all these terms in good time. But as we'll see in this class, oftentimes we can cancel some of these terms immediately. And doing so is going to greatly speed up and simplify the process of doing the problem. So in the remainder of this video, I'm going to teach you several keywords that you can look out for, that if the problem statement says this, you can automatically cancel the following terms. Number one is if no temperature changes, phase changes, or reactions occur. If no T changes, P changes, or reactions occur. Think to yourself, this is going to be one of the 5 terms of the general form of the closed system energy balance is going to cancel and be equal to 0. Think to yourself about which one this means. And the answer to that is that the change in internal energy is going to be equal to 0 because U depends on chemical composition and it depends on the state of matter. So if I don't have anything changing temperature or pressure, I could say that the change in internal energy is equal to 0. That was kind of a hard one to start off with. Let's start with let's go to an easier one. If it says no acceleration, acceleration, which term is going to cancel? And if I don't have an acceleration, that means I'm not changing velocity, and therefore my change in kinetic energy is going to be equal to 0. Remember that I'm only considering translational kinetic energy, not rotational kinetic energy. If the problem statement says no change in height, then my delta Z is 0. And the term that is going to cancel is going to be my potential energy, a change in potential energy. This one's a bit tricky, but if I have temperature of the system equaling temperature of the surroundings, or if it says perfectly insulated, that is going to mean that heat cannot flow from hot to cold. So the first one, if temperature of the system is equal to the temperature of the surroundings, then there is no difference in temperature for the driving force to occur. And perfectly insulated is a term that means that there is no heat that is transferring through the boundary. So when I think of an insulated thing, I think of my water bottle that is vacuum sealed. And it turns out that air is a very good insulator. You'll learn more about that in your transport classes in a future semester. So if either one of these things are mentioned, then this means that Q is equal to 0. And the last one, if there are no moving parts. No moving parts. And this is kind of subjective. No moving parts or system boundaries, then W is going to be equal to 0. No work. And I'll be quite honest with you, in this class, a majority of the times, kinetic potential and work are going to cancel out. And the energy balance is simply going to be of the form Q is equal to delta U. And this is going to be usually what the energy balance simplifies to. And once again, you'd be very surprised at how difficult and complicated this can get. Okay, that's going to be it for this video. I was going to do the open system energy balance, but I think I'm going to leave that till the next video. So for now, let's just leave it at the closed system energy balance, and we'll call it a video. See you next time.